I don't want to do that integral, you don't want to do that integral. So what we're going to do is we're going to use something called an external fractional function. And it is a tabulated version of that integral. It's been done numerically, so you don't have to do it. It's programmed in ease, so you can go just look at the ease function. But the basic idea is that we're going to compute something called f. So f from 0 to lambda 1. That's going to be the fraction of light, or the fraction of energy, power, let's say, that's contained in the band from 0 to lambda 1, that wavelength band. And this function is formally defined as EB from 0 to lambda 1 divided by EB, like the total, right? So there's a spectral integral, and then there's the total in the denominator. So if we write that out, it is that full integral, and it's this thing up here, right, this thing up here, divided by sigma t to the fourth. So if I want to do that integral, if I want to represent it in a way that's helpful, we've got kind of a problem because we have lambda, and we also have temperature. So both of those are kind of independent things that we can choose. Well, it turns out that maybe if we did some manipulation, we could express the same equation in terms of the product lambda times temperature, right? And maybe it's not obvious why, but if I make the substitution, u is equal to lambda t, and then I need to compute somehow d lambda, because d lambda appears up here. D lambda is going to be du over t. So knowing these things, I can make that substitution into that integral that I've got up there. And we end up with this integral. So it is f from 0 to lambda 1 is equal to the integral from 0 to lambda 1 times temperature. So now we have this nice product of lambda and temperature where before we just had lambda. And then the equation over here becomes C1 over sigma times the quantity lambda times temperature to the fifth times exponential of C2, C2 over lambda times temperature minus 1 d lambda t. So why did I do that? Just to prove to you that if we make this substitution, I now have this entire expression in terms of the product lambda times t. And that's important to you because when you evaluate the fractional function, this external fractional function, it requires you to provide it the product lambda t. Right? So this plot here is product of wavelength and temperature, lambda t. Lambda t. So if I'm going to use this, what I'm going to do, let's say we want to just do a quick example here in the last couple minutes. So what I would do is, let's calculate the amount of radiation that falls in the visible spectrum from the sun. So I want to figure out what fraction of the total light coming from the sun, the total power coming from the sun, can I physically see, right, if I have good eyes, right? So that would be calling this external fractional function f. And I'm going to evaluate that first at kind of the upper bound of radiation, or of wavelength, and then at the lower bound. So what I mean is we want to look at like f from lambda 2 times temperature minus f from lambda 1 times temperature, where temperature is the temperature of the sun. Right? And if it's not clear where that came from, let's just scroll up a little here. What I'm saying is I want to calculate basically what's falling in this green region, okay? So I can see what's in that green region. So this would be lambda 1, this is lambda 2. So I'm going to evaluate this fractional function twice, both from 0 to lambda 1 and then from 0 to lambda 2, subtract the 2, and then I get the difference between those two, right? So that's kind of what I'm doing here. Okay, so we're taking this example. It turns out the visible spectrum is about 0.38 micron up to about 0.78. Okay, and we know the temperature of the sun is 5,800. So I just take this and I say, okay, I'm going to do f at 0.38 times 5800. Or sorry, 0.78 first, right? 0.78. Minus F at 0.38 times 5800. And this evaluates to 0.56 minus 0.14, thereabouts. Oh, sorry, it's not 0.14, it's 0.1. And that ends up equaling 0.46. Okay, so what that's saying is that 46% of the light that's emitted from the sun is something I can actually physically see. Okay. All right, that's it for today. Thanks.